The radio call came in at 7:12 in the morning on an ordinary December day. Salt air, light seas, the kind of patrol that generates no paperwork and leaves no memory. The Atlantic Star was running its standard sonar sweep just off Deerfield Beach when the numbers stopped making sense. The sonar should have read 12 feet. It read 40. Lieutenant Commander Ethan Miller, a 19-year veteran with a background in hydrographic survey, ordered a second pass, then a third. On the third sweep, the multi-beam echo sounder mapped something that had no business being there. A 300-foot void, perfectly circular, its walls sheer limestone, its bottom vanishing into darkness beyond the instrument's range. The ocean floor simply was not there anymore. Miller keyed the emergency broadcast channel. His voice was steady. What he said was not. Depth anomaly. Possible collapse. All vessels clear the area. The bridge received immediate clearance to escalate. At 7:48, his formal incident report filed with the Coast Guard used the word no one in the Florida Coastal Authority had ever written before in an official dispatch. Unprecedented. No earthquake had preceded it. No storm, no underwater landslide, no tremor registered on any instrument along the coast. A section of Florida's limestone bedrock, the very foundation on which the state was built, the rock that had held for thousands of years beneath one of the most developed coastlines on Earth, had simply let go. The archival survey data made it worse. The same coordinates examined last spring showed a gentle, sandy slope, no cavitation, no sign of stress. What existed in the spring as solid ground had, overnight, become a chasm with no measurable bottom. What troubled Miller most was not just the size of the void, it was the speed. Reviewed frame by frame, the Coast Guard's own sonar logs revealed the collapse had occurred in less than a single tidal cycle. There had been no slow deterioration, no incremental warning. The ground had held, and then it had not. The void was not static either. With each new sonar pass, the readings shifted. The cavity was growing in real time, its edges creeping outward as Miller's crew held station and watched, running grids as far as the equipment could reach. No one on the bridge said what everyone was thinking. If the limestone beneath Deerfield Beach could vanish overnight, what else was at risk along this coast? Within 90 minutes of that first ping, the Atlantic Star was no longer the only vessel tracking a crisis. A second breach appeared off Pompano Beach, this one measuring 450 feet across, 50% larger than the first. By 8:15, a third collapse registered near Boca Raton, spanning 380 feet. Reports from the shoreline described sand and water funneling downward in slow, silent cascades, entire sections of beach pulling inward and disappearing with a sound that witnesses compared to a long exhale. By noon, there were 23 confirmed sinkholes. By the time emergency managers began counting the cost in dollars, $2.3 billion before lunch, the more fundamental question was still unanswered. What, exactly, is happening to the ground underneath Florida? The aerial survey teams scrambled at first light, flying grid patterns at 500 feet and relaying live images to the state's Emergency Operations Center. Data analysts overlaid sonar and satellite data, tracing the outline of each new cavity as it appeared. The pattern that emerged was not random. The sinkholes formed a linked chain, each new void opening within minutes or hours of the last, following a rough arc that paralleled the coastline for 15 square miles. It was as if the limestone platform was not failing in isolated pockets but unraveling along a seam, one section pulling the next into collapse behind it. 23 holes in less than 5 hours, a rate that had no precedent in Florida's documented geological history. By early afternoon, entire sections of beach, parking structures, and the ground floors of several oceanfront buildings had been swallowed. The official maps, updated every hour, showed a coastline transformed. What had been a continuous stretch of sand and concrete was now a chain of voids, each one threatening to pull the next segment under. Emergency managers ordered the immediate evacuation of every beachfront hotel and residential tower within the hazard zone. Police closed the coastal highway for the full length of Broward and Southern Palm Beach counties, rerouting traffic onto inland roads already choked with vehicles. Displacement numbers climbed fast. By the end of the morning, 12,000 residents and tourists had registered at temporary shelters. Thousands more were still waiting for transport, standing in parking lots with suitcases, watching the sky over the water darken with the smoke of emergency generators. Dr. Lisa Hernandez has spent 20 years studying Florida's karst geology. She was among the first scientists called to the state's Emergency Operations Center that morning, and by afternoon, she was standing before a rotating three-dimensional seismic model of the southeast coast, pointing to a single data column that has since become the most consequential number in Florida's geological history. 0.45 millimeters per day. That is the current rate at which the limestone beneath this region is dissolving. The historical average is 0.02 millimeters per year. Read those two figures side by side and let them settle. The rock is not degrading on a geological timescale anymore. It is degrading on a human one. The chemistry driving this is not mysterious. It has been documented, modeled, and published. What was not anticipated was the convergence of forces arriving simultaneously at this magnitude. Rainwater, naturally acidic from absorbed carbon dioxide, has always seeped into Florida's limestone. For millennia, this produced a slow, manageable dissolution. But when that fresh acidic water meets saltwater pushing inland from below, driven by 3.2 millimeters of annual sea level rise above the global average as recorded at Miami Beach, the reaction changes character entirely. The resulting mixture is carbonic acid at concentrations far more aggressive than either component alone. Hernandez's laboratory analysis found a 40% increase in rock porosity wherever saltwater intrusion was highest. The stone is not simply dissolving at its surface. It is being hollowed from within, riddled with microscopic channels that widen with every passing season until the structure above has nothing left to rest on. Thermal stress adds another layer of damage that compounds daily. South Florida's temperature swings, amplified by exposed bedrock and shallow groundwater, drive microfractures through the limestone at a rate of 0.12 millimeters of expansion per degree Celsius. These cracks are invisible to any surface survey. But over months and years they multiply and connect, opening new routes for acidic water to penetrate deeper into the rock. The platform that appeared solid from above was, in the language Hernandez used at the briefing, quietly becoming Swiss cheese. Her team's seismic survey, completed in partnership with the University of South Florida, maps a cavern network running continuously from Miami to Jupiter. Some of those chambers reach 200 feet in height. Their walls are etched smooth by the relentless action of acidic water moving through them over decades. These are not isolated geological curiosities. They form a branching, interconnected system running directly beneath neighborhoods, beneath highways, beneath the water and gas lines that keep millions of people alive. The collapse frequency in the region has reached 12 new sinkholes per week. The historical average was 2 to 3 per year. Maria Martinez has unlocked the doors of her family's restaurant every morning for 26 years. She grew up watching her grandmother work those same hours, memorized the particular drag of the key in the old lock, knew every table by the initials scratched into its underside by her children. She did it again this morning out of habit, out of the refusal to believe that a morning could be different just because it looked the same. By noon, the building was condemned. A structural inspector, one of dozens deployed across the evacuation zone, had flagged the foundation as compromised. Her three-generation business, appraised at $2.8 million and anchored in this neighborhood since before she was born, was removed from the tax rolls in a single afternoon. Her insurance adjuster's email arrived before dark. It was written in careful, neutral language. It cited a clause she had never thought to read. Ground collapse, not covered. Martinez loaded 2 suitcases, took her grandmother's photograph from the wall, and joined 340 other evacuees from her block. The coastal highway that she had driven every day of her adult life was closed. Traffic on the inland bypass crawled for hours as 45,000 displaced commuters competed for roads built for a fraction of that volume. Sections of the inland pavement had already begun to subside, the damage spreading faster than repair crews could track it. "What do you come back to?" she asked a volunteer at the shelter registration desk. Not accusingly, not with anger, just as a genuine question from someone who had run out of certainties. The volunteer had no answer. Nobody did. By early afternoon, a different kind of alarm had emerged along the waterline. Field crews from the state's Fish and Wildlife Service were collecting samples of a thick black substance coating 12 miles of coast. The volume logged by the end of the day exceeded 2,400 pounds. It had the consistency of cold tar and smelled of bitumen and sulfur. It was not an industrial spill. There was no pipeline in the area, no vessel casualty, no offshore platform. Laboratory analysis delivered a result that nobody in the room had been prepared for. The material was ancient organic tar, carbon dated to between 15,000 and 50,000 years before the present. It had been sealed inside the limestone since the last ice age, compressed and inert in layers deep below the seafloor, and it had now surfaced through the same fissures that were consuming the ground above. Methane detectors deployed across the collapse zones registered concentrations spiking to 0.8%, far above the regional background and well into the range that raises serious concerns about air quality and combustion risk. The gas had been trapped inside the limestone for millennia, locked into ancient organic pockets that no geological survey in the modern era had reason to probe. It was now venting freely through the fractured rock, rising through the water column and dispersing into the air above beaches that, just that morning, had been crowded with December tourists. The ecological consequences were immediate and severe. By dusk, wildlife responders had documented 47 sea turtles coated in tar, several of them unable to surface properly, their flippers and nostrils fouled with the black material. 12 dolphins were recovered, showing signs of respiratory distress, their behavior erratic, their breathing labored in ways consistent with both methane exposure and ingestion of the tar substance. Rescue and rehabilitation centers across the region were overwhelmed within 48 hours, forced to triage incoming cases as new reports continued arriving from as far north as Jupiter Inlet. Beaches across 31 miles were closed to all swimming by emergency order, the first closure of that scale and nature in Florida history that had nothing to do with a hurricane or an algae bloom. Professor James Whitaker of the University of Florida's Geochemistry Department, briefing state officials that evening, was direct about what the TAR and the methane represented. They were not byproducts, they were evidence. The same failure that had opened 23 sinkholes in a single morning had also torn open a chemical archive sealed since the last glacial retreat. "We are not just losing coastline," he told them. "We are exposing a record that has been locked away since humans first set foot in this peninsula." The limestone platform beneath Florida does not stop at the state line. It is the same continuous porous rock that extends northward for nearly 1,200 miles, forming the geological foundation beneath cities, highways, rail corridors, and critical infrastructure all the way up the Atlantic seaboard. What happens to it in Southeast Florida is not contained within Southeast Florida. The pressure changes induced by a large-scale collapse propagate through the connected system, stressing cavities and channels that may be hundreds of miles away. Engineers and geologists have understood this in theory for years. They are now watching it in practice. Lloyd's of London reclassified 47 miles of Florida shoreline as an extreme risk zone within days of the first collapse. Within a week, 340,000 property insurance policies had been voided or suspended across the affected counties, leaving homeowners and business owners facing uninsured losses with no mechanism for appeal. The projected cost of immediate stabilization work, the grouting, the drainage rerouting, the structural reinforcement of the most critical areas has already exceeded $25 billion, and those estimates carry no guarantee of long-term stability. They are, in the language of the engineers producing them, best-case interventions against a process that has not stopped. The Federal Nuclear Regulatory Body issued a formal vulnerability notice for 3 nuclear generating stations built on the same dissolving limestone formation: Turkey Point, St. Lucie, and Crystal River. Engineers at each facility scrambled to review foundation integrity assessments that, until this week, had been considered settled science. The regulatory assessment warned that ongoing subsidence could compromise cooling water intake structures and emergency egress routes. The two systems that, in a worst-case scenario, stand between a functioning plant and an uncontrolled event. Meanwhile, satellite-based ground deformation mapping confirmed that the Port of Savannah, the third busiest container port in the United States, is sinking at 1 centimeter per month. The cranes that move tens of thousands of shipping containers annually, the fuel storage tanks that supply the southeastern fuel distribution network, the dock infrastructure that connects American commerce to global supply chains, all of it now rests on ground that is measurably, verifiably less stable than it was 12 months ago. Structural geologist Dr. Mark Alvarez was standing beside a portable seismograph on the beach when a magnitude 2.8 tremor registered beneath his feet, the 17th such event recorded in Florida that month alone, in a state that sits on no known fault line and had, before this year, recorded almost no seismic activity of any kind. He radioed his assessment to the operations center without inflection, the way scientists report data that frightens them. The collapse front, he said, is advancing northward at approximately 3 meters per day. 3 meters per day. It is not a fast number. It would not alarm you if someone said it about a weather system or a tide. But applied to the dissolution of bedrock, to the northward migration of a failure front moving beneath cities and nuclear plants, and the arteries of American commerce, it is a number that changes the meaning of every structure it approaches. It means the ground you are standing on today is not the ground you will be standing on next year. It means the question is no longer whether this spreads. It is only how far and how fast and what is in the way. The illusion of permanence is gone. In a state built on shifting rock, certainty is now the rarest resource. The sonar readings keep shifting. The void is still growing. And somewhere beneath the highway you drove in on, the chemistry has already begun.